So, hello and welcome to my course on Introduction to Quantum Theory and Technologies. I'll be your lecturer. My name is Tim Byrnes. I'm an assistant professor of physics here at NYU Shanghai. So currently I'm actually in Tokyo. As you are all very well aware, we have to do at least the initial part of this course by video. So the way that I envision this to sort of develop is that, so I will be basically doing the lecture component by video, and I will try and post the videos of each lecture about approximately a week before the actual lecture. And then during the lecture time, perhaps we can meet over Skype or Zoom, some kind of suitable technology, and we can just go over a little bit of the lecture. So what generally I'll expect is that you would have already watched this video, which I'm recording now, and then there will be basically just a short discussion. This would not take the full 1 hour and 15 minutes, because of course you have to view the video. But we can just sort of go over a few questions or any other things that you might have questions about. So for today, what I'll be doing is to firstly go through just the syllabus, just sort of the formalities of the course, so you know how this course will be structured. And then I will give you a bit of an overview of basically what this course is about, very sort of broad brushstrokes, what is sort of quantum technologies, what is quantum theory all about, and then later on this will set us up for looking at various, the actual details of quantum theory. So, so without further ado, so let me just go through the syllabus with you. I should turn that off. There you go. All right. So, okay. So of course, once we start the in-person lectures, we will be in room 523, of course. But until then, we'll be doing this course online. There are no recitations for this course. Again, office hours, once things resume sort of normality, then I am available in room 1200. I think it's better if I use it, at 4:30 to 6:30 every day, so you can pop in. Actually, this is where I do my sort of daily meetings with my research group, and so you may see sort of some other research students around, but don't worry about them. Please just come into the room, and then I can discuss questions with you. In fact, sometimes I might even get some of my students to help you with some of the other, like your homework, for example. Certainly for the time being, this is probably the best way that you can contact me over email. So send me an email if there's anything that you want to ask. Of course, website is available, NYU classes. I'm sure you're all very familiar with that. So at the moment, I've only uploaded just the syllabus and a brief course description, but eventually I'll be adding more and more materials. For example, your homework will be uploaded to the materials section of the site, and any other sort of relevant material. As for the prerequisites, I've made actually calculus the prerequisite of this course. Actually, there's not really very much calculus in this course. It's actually much more based on linear algebra. I'm not sure how many of you will be familiar with linear algebra. So in the first few weeks, I will be doing sort of a crash course on linear algebra, complex numbers, things like that. normally quantum mechanics does involve a lot of calculus, but I actually changed the way I sort of structured this course a couple of years ago, so that I've eliminated a lot of the calculus, which actually makes the technical aspects of quantum mechanics sort of much more simpler. So, I've still made it a prerequisite because there might be some kind of calculus, but really, actually, the main point is that you are somewhat, not afraid of using mathematics, because this course will be a little bit mathematical. That's actually inevitable if you really want to study quantum theory to sort of any kind of serious level. This is, of course, just an introductory course, but I want to actually sort of show you really the nuts and bolts of the theory and how it all works. And to do that, you really need to be able to be at least a little bit comfortable with mathematics, and hence the prerequisite. So the textbook is Nielsen and Chuang's Quantum Computation, Quantum Information. Actually, for this course, I don't really sort of follow the textbook in a very linear fashion. I'm kind of teaching this sort of really the way that I think quantum theory should be taught at this kind of level. I'm not actually aware of any really good textbooks that do this. There might be some now because it's a very popular field, but at least this textbook does cover basically all the material that you need, but it's also something like 700 pages long, and I must admit I've not really read it cover to cover, so really it's more like a reference book rather than a textbook that you would learn off. I think certainly you can, it's a very, very good textbook, but it's not something where I'm just going to sort of follow exactly, and so this is why this is actually just a recommended text. It's not a required text. There are actually no required texts for this course. Another very good textbook on quantum mechanics is this Introduction to Quantum Mechanics by Griffiths. This is also kind of a very standard textbook on quantum mechanics, but it's actually kind of much more detailed than you really require for this course. So again, it's more like a reference book rather than kind of something that the course will strictly follow. So my main course goals here is, this is a non-majors course, so this means that we're not really going to be doing, all the same kind of material that you might do in a physics quantum mechanics course. But I want you to just basically appreciate how sort of quantum mechanics works at kind of a elementary level, and this is really enough so that you know all the kind of pieces of quantum theory. I mean, basically everything else is just extensions and more complicated versions of this. So you will actually understand quantum theory to sufficiently high level so that you would actually really have done quantum mechanical calculations and really know what things like quantum computing and these emerging quantum technologies are. So this is sort of my goal, to kind of show you this material in a relatively simple way so that you can sort of appreciate quantum theory and quantum information at a level that's not just sort of like a Mickey Mouse level where we just sort of say, oh, quantum mechanics, you can be in two places at once, and isn't that mysterious? And a lot of the time, especially in the media, quantum mechanics and quantum information is portrayed in this way, where it's kind of portrayed in a rather mysterious sense, but the aim is to sort of show you really what it's really about, so not some watered down version. Okay. The kind of topics that I will go through are something along these lines. Really depends on how fast we can progress through the material. I don't like to go through the material, really fast. I want you to really understand it as we go. So we start from kind of historical introduction, which is sort of traditionally how you start. Actually, historical introduction is not actually a really good way to learn it. The way that quantum mechanics was discovered kind of follows a course that is probably independent to how you should actually learn it. So, but nevertheless, it's still maybe a bit interesting to know some of the early history. I'll take you through the sort of the necessary mathematics. So this kind of linear algebra and complex numbers. This is kind of really fundamental to the theory. So we really need to understand those to a certain degree. So I will take you through that. Things like the wave function. I think I will probably not go through some of these topics like the Schrodinger equation because I think it's not really completely necessary to learn this, but certainly things like the probabilistic interpretation and other quantum technology aspects such as the physical implementation, qubits. This is what future quantum computers will be based on, how measurement works, and then we can get onto some sort of rather cool stuff where you can do things like quantum teleportation, perhaps cryptography, we can get that far, and other types of future applications of quantum mechanics. So, as I said, this list is probably much more than what we'll cover in reality. So this, don't take this as all the things you need to learn. This is sort of the area that we'll be doing. So, of course, before each exam, I'll specify exactly what you need to know. As for the grading, there will be 2 exams. So there will be the midterm exam, final exam. These are weighted in this way, so of course there's a lot of weight on the final. The final will sort of cover the whole content of the course. Homework will be quite a significant part of the weight of grading, so please do take enough time to do the homework and hand them in on time. And the homework will be uploaded to NYU classes, and this will be basically due each lecture. So I will hand out the homework for the first week. So the first homework will be due in the second week of classes. Okay, assignments I could give as sort of extra credit, but actually in the past years nobody has really opted to do this, so so perhaps that's only if you're especially interested in the topic. And other expectations are more or less just common sense, but so, well, obviously in the online phase the lectures will be online, but as I said, sort of each week we might do a brief Skype or Zoom session so that you can, so I can check in and you can have the opportunity to ask questions. Particularly, that will be the main opportunity, considering the office hours will only begin until after I return to Shanghai. The more questions that you ask, the better. So I'm happy to sort of expand on any other topics that you are interested in, and various other policies such as late work, so 5% of the mark deducted per day. And please don't do anything like copy each other's homeworks. This is taken very seriously. Okay, so that is about it for the syllabus. So I will now start basically just the first part of the course, which is the overview. These slides are of course available also on NYU classes. So the way I sort of expect you to be looking at this video is you can sort of have the video sort of shown maybe in the corner of your laptop, and then you can look at the slides that have been uploaded to NYU classes. Okay, so firstly I want to give you, as I said, sort of an overview of this whole course. So, or really rather the whole topic of what is quantum theory and quantum computing. Recently there's been a lot of media attention and excitement in the field of particularly this quantum computing. So it so happens that right now is might be sort of the golden period of quantum computing. So what I want to do here is just sort of give you a little bit of a flavor of how things are progressing, and really what is special about quantum theory. So firstly, so quantum physics. So what is quantum physics actually? So essentially I would define it something like this. So it's the sort of the theory of nature at small scales, low energies, for microscopic particles like atoms, light, electron, but actually anything small really. So it's interesting that there's sort of one theory that can capture pretty much all of matter and energy and any kind of small phenomenon, regardless of basically what the particle actually is. So quantum theory doesn't really care so much about what kind of particle it is. So it could be an electron or an atom. Basically all these different types of particles all obey quantum physics, and it tends to work for things which are extremely small, and it's quite interesting that of course our bodies and everything that you see around you is composed of atoms, maybe also light, but these kind of microscopic particles. Basically all these things are all determined by quantum mechanics, and it turns out that quantum theory is one of the most successful kind of theories that's actually ever been invented. So you can calculate properties of atoms and things like that to incredible precision. But at the same time, it has some sort of puzzling aspects. So you can write down the mathematical theory of quantum mechanics, but intuitively there's a lot of puzzling aspects which still confound modern day physicists and philosophers. So I've done collaborative types of projects with philosophers. For example, Brad Westlake, which who's a philosophy faculty here at NY Shanghai. We've done sort of a kind of collaborative project trying to understand some of these puzzling aspects of quantum mechanics. So it's even though this theory has been around for over 100 years, it's still got questions which are sort of unanswered. So this is what also makes it something extremely fascinating to actually study. So maybe the archetypal system which obeys quantum mechanics is this one. So this is a picture of an atom. So an atom has some nucleus, it's got protons and neutrons, and it's got electrons orbiting it. And before quantum mechanics came along, this was one of the kind of pictures that people thought, this is what an atom kind of looks like. Looks a bit like a solar system where, you've got the nucleus and these electrons orbiting it. Eventually people realized that actually that picture of the atom is completely wrong, because essentially you really cannot picture an atom to be something involving orbits of electrons. Nevertheless, we still sort of have that mental image of an electron because of an atom rather. Well, because I guess it's sort of is sort of a powerful image of essentially what should be happening. But in reality, what an atom kind of looks like, perhaps a little bit more realistically represented by this. So again, you still have the nucleus in the middle, and the electrons are sort of indeed somewhere on the outside of the atom. But the actual orbits or something about these electrons going around really can't be depicted like that. What it more looks like is these electrons you can't really pin down where the electron actually is. So more realistically, the electron is sort of somewhere within this region. And so, for example, this is like one of the electrons that's closer to the nucleus. It has this sort of fuzzy cloud kind of picture to it. And what that means is that if you try and sort of pinpoint where the electron is, you can never really do it. It's sort of just somewhere in there, and that's basically the best that sort of you can kind of picture it. So this picture is already a little bit mysterious in terms of our classical kind of world, which is so by the way, quantum physicists like to distinguish things which are based on quantum theory as either quantum or things which are not quantum mechanical. So things like our everyday lives, driving in a car, throwing a ball, Newton's laws, planets orbiting the sun, all that kind of stuff we consider to be the classical kind of world. And this would be a kind of a classical picture of an atom, but more realistically, you have to think in terms of quantum mechanics if you want to understand all the properties of an atom. And more realistically, it's kind of this kind of picture. So the main message here is that the electrons that are going around, you really cannot imagine to be sort of located at some precise position at a certain time. These are sort of more delocalized and sort of occupy the whole space somewhat all at the same time. This is kind of a heuristic or some kind of way of picturing an atom. So how people how this theory developed is so Erwin Schrödinger, which is one of the fathers of quantum mechanics, so in very early 20th century, wrote down basically the fundamental law that that determines quantum mechanics, and this is named after him. It's called Schrodinger's equation, and for a single particle, it looks like this. So what Schrödinger basically wrote down was an equation that tells us basically how these quantum mechanical waves change in time. So the way that we describe an electron is then, so classically what we would be doing when we describe like an electron is we say, okay, at time equals to 1, the position of the electron is here, right? And then at time equals to 2, the position of the electron is somewhere else. So what Schrödinger basically said is that, well, you can no longer really say that the electron is at, point at time 1 it's somewhere, at time 2 somewhere else. We have to always describe the electron by some kind of wave. And so this function here, this psi function, is basically this so-called wave function. So it's a function. It depends on space. So it's some kind of shape in space. So a wave can be all kinds of different shapes, and then this changes in time. So this is a real life kind of evolution of one of these wave functions according to the Schrödinger equation. It's a complex number. It has a real and an imaginary part, which we'll talk about more later. And so, for example, this wave function would be something where it would be like, could be an electron, for example, and it's like moving from left to right. But more or less, you can say that the electron is sort of at this position, but again, just like in that example with the atom, can't really say that it's at exactly, say, 3, or, can't really say it's exactly at 2 or 2.5 here. It's got a bit of a spread, and this spread is kind of moving along together. So this equation is really like the fundamental equation of quantum mechanics, and its role is a lot like sort of Newton's laws, for example. So Newton's laws, what you learn in, say, high school physics or first year physics is that you have Newton's laws, and in principle, if you've got Newton's laws, then you can calculate anything. So if you throw a ball, then it will predict that the ball will fly up, it will fly down, and it will hit the target. Or maybe a more modern example is like when you're playing games, computer games, then if something hits another object, then the way that the objects on the screen behave are determined by the laws of physics, and actually you would use Newton's equations to work out how things move around. So there are physics engines in computer games. So this would be like the Newton's laws version of quantum mechanics, right? So this tells you how everything changes or evolves in time. So if you know what it is at some initial time, then this will tell you how everything evolves thereafter. So, so just to see a kind of the difference between quantum mechanics, so and classical physics. So the we just go back to this example, apart from the fact that this is like a wave that's moving left to right, and I said that you can't really say whether it's exactly at 3 or 2, but more or less it's essentially in this region. So apart from the fact that it's a wave, you might say, well, okay, it's a wave, but it's more or less moving left to right. So this might describe something which is just a ball which is moving left to right, and there's some kind of complicated stuff happening in the middle here, but if we don't worry about that so much, then it's it's not so different to classical physics. So this is sort of a different example where you do see something quite different to classical physics. So if you have classical physics, there's a golf ball taking in slow motion. I chose this example mainly because it looks kind of cool. There's not really so much significance to all the wobbles that you see in the golf ball. But the main point that I'm trying to make here is that if you throw a golf ball against the wall, then what will eventually happen is that the ball will hit the wall, but it will bounce back, obviously, right? Now, if we do actually the same kind of thing with quantum mechanics, you see something a bit different. So this is more or less doing the same thing. You have maybe a microscopic electron, and you're hitting it, and here's a wall. And Schrodinger's equation that I showed you on the previous slide can describe this kind of phenomenon. So the electron comes in, it hits the wall, and if you just look at this part, it sort of bounces back. So that part is very similar to the classical physics. But what's interesting is that there's actually a bit of the wave that actually goes through the wall as well. So this is called, this has a name, it's called quantum mechanical tunneling, and it tells you that there is some kind of probability that the ball actually will go right through the wall and emerge on the other side. Now, that probability gets extremely small depending upon, say, the thickness of this wall, also the energy of the electron in comparison to the kind of energy barrier that's present, provided by the wall. But nevertheless, there's a small probability that will happen. Now that never ever happens with classical physics. So this is already a particular example where quantum mechanics actually can predict something that's quite different to classical physics. So to take it to the extreme, what this would say is that if I walked straight at this wall here, then there is some chance that I would just pass right through the wall and emerge on the other side. So why is that? Well, because my body is made of atoms. Okay, so this process could just happen to every atom in my body, and then that could is a possibility. But of course, that's a very unlikely kind of event, which actually shows another effect of quantum mechanics, which is it's actually kind of a probabilistic theory, and it deals actually in probabilities. So this is basically what the meaning of this is that, so when this electron or particle that comes here, there's a portion of it that reflects, just like the normal classical case. Then there's a portion of it that actually goes right through. And so at the moment, this actually looks like it's gone through and it bounced off sort of both of them at the same time. And that actually is what quantum mechanics predicts. But if you go and measure it, basically what you'll see is that it'll either have gone through, or it would have either reflected, one of those cases happens. So, but the main point here is that sort of quantum physics can give different results to classical physics. And essentially what, one of the main differences is really that quantum mechanics is something that deals with waves, and classical physics always considers things to be based on particles. So this is just to illustrate this point. So if I asked you, where is the shark in this picture? It's not very clear in this projected picture, but there's a kind of a shark somewhere, I believe, right there. So, of course, saying where the shark is that you could say it's right there. But if I said, where's the wave? You would immediately say, well, the wave is, all of that is the wave, The question actually is not an appropriate question, because if you are saying, where is the wave, it does not have like a precise sort of answer. Like, all of this is the wave, so it's kind of the wrong question. Whereas the shark does actually have a kind of an answer. It's right there. So the point here is that there are, you might actually be, some of the mysterious aspects of quantum mechanics can occur because you sort of ask the wrong question, because whenever you make a question, sometimes, there are assumptions that you make in the question which make the question kind of a nonsense question, because it's incompatible with what is really happening. So this kind of the strange things that you might see with when you say that in the atom the electron is in some cloud. Basically, this is the consequence of having a wave theory, because the electron is sort of everywhere. It's in a wave, and it is sort of delocalized around the atom. So if you say, where is the electron, it's again sort of the wrong question. In a way, the right question is, okay, what is the form of the wave of the electron, right? But of course, that if you ask that question, then you would already know a little bit about quantum mechanics. Okay, so the point is that things can be, in quantum mechanics, it's quite natural for things to be in sort of two places at once. So this is sort of an experiment that you might consider doing. So we have like an electron, which is coming here, and we might have some kind of small barrier, some area in the circular region where the electron is not allowed to enter. And then so the electron has to choose whether it goes left or right. Now, of course, if you were playing, pinball or something, which is a little bit like this, then if you had some big ball, then it would either go left or right. Maybe it's kind of random, but it would go left or right. Quantum mechanically, it's perfectly reasonable that the electron can actually go both directions at once. And if the electron goes both directions, then essentially this is because the electron is actually a wave. It can actually sort of be in both places at once, which is, it's a consequence of the wave nature of particles. And when they recombine, they can just, again, sort of form the one kind of location. But what people see is, or if you did this experiment, is actually when you see this recombination, there's some kind of wave interference that occurs. And if you're familiar with interference of waves, this is just like how waves always occur in, even with like water waves or sound waves. If you have a wave and both of them are sort of in phase like this, then you get sort of a doubly large wave. But if you have two waves where the crest actually matches the dip of the wave, then you can actually cancel out the waves, right? This is how like noise cancelling headphones work. So when you put your noise cancelling headphones, what it actually is doing is it's detecting the sound that is coming from you. So you're in your airplane and you've got your noise cancelling headphones on. What it's doing is it's got a microphone, it's detecting the sound that is coming around it. It's emitting this thing that exactly cancels it so that you have some peace and quiet on your flight. So that effect also happens in quantum mechanics, where if you've got two quantum mechanical waves, they can actually meet, they can either cancel each other or you can get a doubly big wave. Right? But what's interesting is that actually, in this case, the electron actually is interfering with itself. So it's actually really in two places at once. You can actually really do these types of experiments in the lab where electron interference occurs. So this is something like some semiconductor material, and this is 200 nanometers, which sounds quite small. It's about 0.2 of a micron. Micron is 1,000 times smaller than 1 millimeter. So obviously this is much smaller than you can see, but you do see exactly these kind of constructive and destructive interference effects. So this electron, in this case it's an electron, and you can control the electron's trajectory by all these electrical gates that you can create, and then you really can see these kind of constructive and destructive interference effects. So it has these wave properties. So if that was the end of the story, you might say, okay, well, fine. We've been thinking about particles always all wrong. Everything is a wave, fine, everything's a wave. But what's interesting is that it still has some kind of particle-like effects. And the way that you can still sort of see this is, so for example, if you send electrons at this kind of double slit pattern, that double slit here, you see, again, the interference effects. But what actually happens is that these electrons, it's not like you see these interference effects straight away. You can actually build up this this kind of pattern, kind of electron by electron. So you can send like one electron at a time, and if you just send one electron, you just see like one of these dots here, and it would just kind of randomly come out. But then if you did that thousands and thousands of times, then you start to actually see the interference effects. So there's a kind of a strange dualism that you see, that it certainly has the wave properties because you do see these, interference effects. But at the same time, you actually still have the particle effect, so that you only actually detect one particle at a time. So it's basically got features of both, and how this can be true is still something which a lot of people have difficulty getting their heads around. So this is called wave-particle duality. Other kinds of quantum mechanical weirdness. So already wave-particle duality is something which people thought was very weird since the beginning of quantum mechanics. Another very weird kind of effect is so-called entanglement. So entanglement is what Einstein called kind of a spooky action at a distance. And we'll talk about this more in the lecture later, but in this case this always involves, say, two particles. And what can sort of happen is that the particles can be sort of intertwined twins of each other, so that if you made two particles that are entangled, they're in a special quantum state, and you detect whether this particle is in this one of two states, which are denoted by this up or horizontal arrow. You might actually do this with polarization of light. So, for example, the polarization of the light is going up or it's going across. Now, you can create states such that if you detect it in one of these states, then basically this will always come out in the same state. If you detect it in the horizontal, then this will always come out in the horizontal state. And what's interesting is that people actually showed that this, before you detect it, it really does not have either of these states. It's only because you measured it that you collapsed it into one of these states. And somehow what you measured can affect the other particle. And this can happen regardless of how far these things are separated. So, so for example, these particles could be on different galaxies, and how you measured it here mysteriously changes the state accordingly, so matches it exactly. It's like a copy of it, and that can happen, across light years, and it can happen instantaneously. And this is extremely strange. How can that possibly happen? Einstein thought that there's something wrong with the theory, but it's being verified that this really happens. So there's some strange effects here which, again, people can perfectly write down the theory, but it just doesn't seem to make any intuitive sense. So another kind of famous paradox is the Schrodinger cat paradox, where you can have apparently, if particles can be in two places at once, or an atom could be in two states at once, then what you can have is you can have some contraption. So, for example, the state of the atom could be linked to a Geiger counter, so that if the state of the atom is in one of the states, then this eventually triggers some mechanism to smash some bottle, and then it kills the cat. And if it's in the other state, then it doesn't do that, so that in that case the bottle is not smashed and then the cat lives. So apparently, quantum mechanically, you would write that as a state of the cat being in both the alive and dead states at the same time. And so Schrodinger pointed out that, well, how can this be? Our theory is clearly predicting nonsense, that a cat can be alive and dead at the same time, so there must be something seriously wrong with the theory. But in fact, that is, well, the theory is like that. Things have developed since then, so somehow I think this is no longer thought of as a great paradox, but if you take things to the extreme, then indeed this is what you would write. But we'll talk about this point a little bit more later. So more on the technological aspect. So what is increasingly becoming clearer is that things like Moore's law, this is the law that states that the number of transistors on a computer chip doubles every 18 or 24 months. And this law has held very well, actually, already for many decades, something like since maybe 70s or even earlier. But there's kind of a limit to how many transistors you can really kind of squeeze on to a computer chip. And so back already 7 years ago, one of the chief architects of Intel was saying this year is a year that Moore's law would be dead. In fact, I think it's already, the signs are that already Moore's law will be coming to an end. So the sort of the age of computers where you can always buy a faster computer, in terms of the number of transistors, is already sort of coming to an end. So there's other sort of very similar laws, but really what's the fundamental problem, or why we can't just keep on making faster computers, is essentially over the last several decades the speed-ups in computing have happened because you can increasingly miniaturize the circuits. But the problem is that the transistors and the structures that you're making in computer chips are already really getting to the level that is similar to the atomic level. So for example, this is some the smallest 3D transistor that was announced by MIT in 2018. This is about 3 nanometers big. Now, if you compare that to the size of the actual atoms making up the structure, for example, this is indium gallium arsenide, but these gallium and arsenide atoms are 0.36 nanometers. That's only 10 times smaller than that. So actually, this thing is made of something which is only about 10 atoms across. So you can imagine that once your building blocks, which are the atoms, you can't build things smaller than an atom. So we're naturally going to be hitting some limits. So you can take this as sort of a curse, and you say, oh, we cannot build faster computers because we've hit the atomic limit, damn you. But another approach is to say that, well, maybe we can actually do interesting things because we've actually hit the atomic limit. We have now the technology to actually build things pretty much at the atomic scale. Maybe we can actually do really interesting things with that. And so this is sort of the idea of sort of quantum technologies, is to say that, well, we are getting to the level that engineering is so good that you can actually produce quantum mechanical machines. And this is actually quite a novel type of idea. Quantum mechanics started off by just trying to understand nature. So humans were taking a kind of a back seat in terms of what is, nature gives us. So it's like, here's an atom. How do we understand it? Okay, so we've got quantum theory. Now we can sort of predict all kinds of things about it. But if we can actually actively create machines and technology that is based on quantum mechanics, and this is a kind of a new realm. And we're only just really entering this realm. So this is just some list of famous inventions. So here's quantum theory, invented probably, invented in the first few decades. Maybe this is when it was more or less complete in the 1920s. And there are already some things which are, some inventions which are related to quantum mechanics, but still there's not really that many. So things like transistors, semiconductors, we're approaching some kind of quantum limits. In fact, semiconductor materials, in order to really understand them, you actually need quantum theory. But we don't really actively use the quantum mechanical aspects of that. We're just using that as a material. So some of these things are sort of what I call indirectly quantum. So superconducting magnets uses superconductivity, but it just makes a really powerful magnet. So it's not really using the quantum nature of it. So-called squids, this is not things in the ocean, this is superconducting quantum interference devices. These are devices to measure the magnetic fields at an extremely precise level. Magnetic resonance imaging, MRI machines, this is also something that deeply relies upon quantum mechanics. And lasers, this is also something which is really intertwined with quantum mechanics. So I would say that probably these ones in the red boxes and high temperature superconductors, these are the really quantum mechanical kinds of inventions, but still there's probably many more out there, and really there's a whole world of technology that we are still trying to sort of, we're yet to discover. So, we're going from this age of using classical physics, being engineers of the classical world, to make technologies. So, of course, all these kind of familiar things are based on classical physics. But once we are masters of quantum physics, then we might be able to make more and more technologies. And we're just on the edge of that happening right now. And as technologies develop, then we should be able to make more and more of these things which are really using quantum mechanics. So the types of quantum technologies that people are thinking of today might fall into broadly sort of 4 categories. Well, there's probably more and more emerging, but this is 4 examples at least. So this is doing secure cryptography. So if you wanted to communicate with, say, your bank, of course you want a secure encrypted connection. So of course we do that just using the internet, using classical cryptography schemes. But actually these could be broken if you have powerful enough computers. So the idea is we might be able to develop new types of cryptography which are inherently unbreakable, not because your computer is not powerful enough, there's no hacker with a very powerful supercomputer. It's basically because of the laws of physics. There's fundamentally no way to crack the kind of encrypted code. Other applications are extremely precise ways of measurement. You may have heard a few years ago there was great excitement because the first gravitational waves were detected. So this involves some collision of 2 black holes in the universe. It created a massive kind of explosion, I guess, and this created ripples in space-time, which we detected using so-called LIGO detectors. What people are now doing is to actually get even more precise measurements of this using tricks that were developed in quantum mechanics, and you should be able to make even more precise measurements of the gravitational waves using these techniques. Another one is sort of material science, more or less, so to understand the nature of matter at the quantum level. This is a very big field of physics to really understand how materials have particular properties. And so at the same time, this is a very complex problem. So to actually be able to engineer materials at the quantum level will allow you to actually understand these materials to a better extent. And finally, also quantum computers. So this could be potentially applied to all kinds of different tasks, such as database search algorithms, better search engines, quantum machine learning, and again, like sort of factoring numbers, which is related to sort of cryptography schemes. So what's another kind of direction that that people are going is to make sort of like the quantum version of the internet. So recently there was some experiments where you could demonstrate this kind of secure cryptography between say two islands off the shore of Morocco there, and they chose these two islands because they actually have very high observatories. The areas are nice and clean there, and they could perform this cryptography across about 143 kilometers between two islands. So that was already very impressive. But now actually this is already being superseded by various groups, in China, where so the Chinese teams were the first to actually send a quantum satellite, meaning a satellite with this kind of quantum capability into space. So they did this before any country, before the US, before Europe. And this was a fantastically successful program, and they could immediately get this kind of entanglement distribution over much longer distances. So the previous record was 143 kilometers, but after using the satellite technology, they could extend this to something like 1,200 kilometers. So, so people are very excited about this now, and this will undoubtedly be part of the technology to build the future kind of quantum internet, where you could create quantum channels between various positions on the Earth, and much like the classical internet, you could do sort of quantum algorithms through your quantum internet, and this is potentially also a framework to do cryptography, various other interesting tasks. So there's a lot of excitement over in this field. And finally, there's of course quantum computing. So this year, last year, Google, you may have seen some of the news reports that Google achieved quantum supremacy for the first time. So this basically means that you can, this was the first time that they could do a kind of a computational algorithm which was more powerful than something that could be done on a classical computer. So their initial report said something like, whatever they did on their quantum computer would have taken some 10,000 years. I can't remember the number. On the on a classic or on a regular computer, even if you use the most powerful computers, IBM followed up by saying that no, you can do this in a few days, in fact. But this, I think, nevertheless shows that we're just on the cusp of having quantum-based sort of computers, which are actually more powerful than classical computers. So it doesn't really matter that it's 10,000 years or 2 days. The fact that it's much faster than what you could have done on the classical computer is the important point. So maybe it's not quite as much as what Google originally claimed, but still 2 days is quite a long time than what it actually took to do the quantum calculation, which is probably less than a second. The types of technologies that people are thinking about are something along these lines. So this is the technology that Google used based on superconducting qubits. So this is using certain superconducting materials. But there are all kinds of different competing technologies out there. So some people think that using photons is the way to go, so-called ion traps. So this is using ions, so ions are charged atoms. You can arrange them in certain ways on a chip. Quantum dots, this is basically semiconductor technology, even using diamond. Here at NYU Shanghai, our research group also uses sort of an atomic kind of method, so it's pretty similar most to this one. Again, using chips and storing information on that. So there are all kinds of different approaches. We're really still in the early stages of developing this technology, so it's still difficult to tell what is the one that is going to be the eventual version of the semiconductor. If you remember, classical computers started off with vacuum tubes, and even before then, Charles Babbage, which originally had the concept of the computer, tried to make a computer with gears and things like this. It took a long time to hit upon the right technology, which in the case of computers was semiconductors. For quantum computers, now the leader is probably this one, because this is the one that Google uses. But still, I think it's still wide open to know, to still try and predict which one will be the technology that everybody settles down into. Why is a quantum computer faster? Well, it's mainly because of this nature that things can be in sort of two places at once. So in the same way, a classical computer, basically at any one time you can only do one kind of operation. So if you input some data, then the output will be something. In a quantum computer, because things can be in multiple states at once, so you could actually put all this in once, and then there's this sort of massive parallelization that can occur, which has potentially power to be extremely fast compared to classical computers because of this massive parallelization that is possible. Actually, it's a little bit more complicated than this, so I'll try and we'll discuss that in the course. This is sort of like the 0th level kind of explanation of why it's faster. So this certainly comes into it, but it's really not the full story. In fact, I don't think anybody really understands completely how to make a quantum computer always faster than a classical. This is generally not really known. But there are certain instances of algorithms that people do know where quantum computers are faster. As I was saying, there's a lot of commercial interest these days. So this has really exploded in the last say 5 years, with IBM, Google, Microsoft, all these big computing companies entering the race. There's also smaller startups, Rigetti, IonQ. This is sort of a spin-off of a research group. And D-Wave, which started off having a very kind of bad name. People thought that they were not very trustworthy with what their claims were. But these days, I think people are a little bit more open to understanding, or the technology that they have, because there's now a lot of commercial interest, and so there's now is really quite a golden time for this kind of field, with a lot of funding and a lot of interest. Yeah. Okay, so so what I'll do, I think, so coming to sort of the end of this lecture. So after this kind of introduction, what I'm going to do is to give you more of an overview of the kind of mathematics that we'll need to cover quantum theory. So this will be basically things like linear algebra and complex numbers, and hopefully then we'll get on to looking at more of the quantum technological aspects after we've covered the basics of quantum theory. So, so what I'd like you to do here is to basically, so certainly, look at the lecture notes here, and during the first week of class, then we can have a Zoom or Skype session. I'll send the details of that. And if you have any questions regarding that, regarding what I talked about today, that will be your opportunity to ask about it. And basically each week we can sort of repeat that kind of schedule. So I'll upload a video of the lecture beforehand, and during the class time we'll have a short Zoom session. So it will not be for the whole 1 1/4 hours. It will probably be much shorter, but this will give you an opportunity to ask questions. Okay, so thank you for your attention, and let me know if you have any questions. All right, thank you.